Hey everybody, this is Mrs. Johnson. This is MAT 221, Calculus 1. This is section 2.8, which talks about how the first derivative is related to the original function and so forth. So let's talk about their relationship. So what does the graph of the derivative tell us about the original function? Well, what we know is we know that when the derivative is positive on an interval, then f of x must be increasing, and vice versa. So in other words, when the original function f of x is increasing, the derivative, which is the slope of the curve, will be positive. So we know that the derivative curve will lie above the x-axis. Notice that you have always positive values here. Now, the derivative is getting smaller because we know the tangent line is getting less and less negative as it comes towards zero here. Excuse me, less and less positive as it comes towards zero here. But we do know this, that when the derivative is positive on an interval, we know that the function f must be increasing. We also know that when the derivative is negative on an interval, then the function must be decreasing over that interval, which again makes sense. When the derivative is negative, you can see the curve is falling down. And notice the derivative curve, the actual function, the derivative function, is below the x-axis because the slopes are all negative values. The slope of the blue curve are all negative values here, so they all lie below the x-axis. So if it is known that the graph of a derivative, f prime, of a function is as shown, what can we say about the original function f? Well, before we actually answer this one, that if it's known that f of 0 equals 0, sketch a possible graph, let's look and see what does this derivative tell me about f? Well, it tells me that I have a zero derivative, looks like I have a zero derivative at x equals negative 1. And I have a zero derivative at x equals positive 1 of the f curve, the curve I can't see because I'm looking at the derivative curve, the derivative function. And the derivative function, the derivative's output is 0 at 1 and negative 1. Now what does that tell me about the original curve? That tells me that the original curve must have horizontal tangent lines at those 2 points. Now, what else does this derivative curve tell me? It tells me it looks like in the interval from negative infinity until x equals negative 1, the derivative curve lies above the x-axis. And from 1 to infinity, the derivative curve lies above the x-axis. So that means in those same intervals of the f curve, the curve I cannot see, must be increasing. Because when the derivative is positive, in other words, the derivative is lying above the x-axis, the f curve, the original curve, must be increasing. Also, it tells me from negative 1 to 1, on that interval of x, the derivative curve is below the x-axis, which means that the f function must be decreasing on that interval. I also see that the derivative is the most negative at x equals 0. This is indicating a possible point of inflection in the original curve of f, because we know when something is decreasing the fastest, in other words, has the biggest negative value, the largest negative value, or in this case a small value, then we know that the curve must be decreasing the fastest. Now, if I know that the original curve passes through the origin, 0, 0, we could sketch a curve of what that original curve would look like. Here's my derivative curve. My original curve has to be decreasing from negative 1 to 1, increasing from negative infinity to negative 1, and increasing again from 1 to infinity. So my curve looks something like this. All right, so notice things that we said. We said that the curve f must be increasing from negative infinity to negative 1. So from negative infinity to negative 1, the derivative curve was above the x-axis. Therefore, the original curve is increasing. Then I have to have a horizontal tangent line because the derivative was 0 at that point. Then from -1 to 1, the curve must decrease. So f of x must decrease from -1 to 1 and be the most negative, have a point of inflection at 0, 0, which is where I have to pass through the origin. Then I have to have a horizontal tangent line again at x equals +1. So because of the derivative is equal to 0 there, my original curve must have a horizontal tangent line there. And then from 1 to infinity, the derivative curve told me that the derivative is always positive, which is indicating that the original curve is always rising. There's a sketch of my original function. I've actually worked backwards here and found a sketch of the original function from the derivative function. So we say that the function f has a local maximum at x equals -1 because near the values near x equals -1, that output of the function is higher than all of its neighboring values. Note that the derivative is positive to the left of -1 and 0 and then negative to the right of -1. Similarly, here at x equals +1, the derivative changes from a negative derivative to this local minimum where the derivative is 0 to this side of -1 where the derivative is positive again. We'll talk more about this when we get to chapters 3 and 4, but for right now we're just noticing that the derivative is changing sign around the local maximum and the local minimum point. Now, since the derivative itself is a function, we can consider its derivative, which is the second derivative, which we saw in section 2.7, where these are all the different function notations for the second derivative. Newton's notation, Leibniz notation of the second derivative. So since the second derivative is the derivative of the first derivative, then we can use that same notation that we'd say, well, when a derivative is positive, then the function is increasing. So if the second derivative is the derivative of the first derivative, then we know the second derivative must be positive on an interval. Then the derivative function must be increasing on that interval. And if the second derivative on an interval is negative, then we know that the derivative curve must be going down or decreasing over that interval. So let's look at this function and look at the first and the second derivative. Now, what do we know if we are to sketch the first derivative? What I would sketch first are these points right here, where the derivative would be 0 and the derivative would be 0. Here we know that the derivative is going to be positive, but less and less and less. Then the derivative is going to be negative, the most negative about the point of inflection. And then the derivative is going to be positive. So if I sketched my derivative curve, it would look something like this. Notice where I would have a horizontal tangent line on the blue curve, the original curve, the derivative will have a 0 there. And where I have a horizontal tangent line here of the blue curve, the original curve, the derivative curve would have a 0. Now, if I took the derivative of that curve, notice when this red curve, the derivative curve, has a horizontal tangent line, its derivative, which is the second derivative, would equal 0. And notice the first derivative is negative on the interval from -infinity to about -0.2 or so, 0.3 or so. So the second derivative curve should be negative values, negative below the x-axis. We also notice something about concavity of the curves. Notice that the concavity of the graph and its derivative. When the original curve is concave down, notice the derivative curve is decreasing. The derivative is decreasing. Notice the tangent line. Look, really positive tangent line, then less and less as we move our tangent line along a concave down area. Notice the tangent line is positive, then more positive, then more positive as I move through a concave up area. This will always be true, that when I'm in a concave down area, the derivative will decrease, and where I'm in a concave up area, the derivative will increase. So the graph of a differentiable function y equals f of x is concave up on an open interval if the derivative is increasing on that interval, or concave down on an open interval I if the derivative is decreasing on that interval. The graph of a twice differentiable function f of x is concave up on the open interval where the second derivative is positive, and concave down where the second derivative is negative. A point where the graph of the function has a tangent line and where the concavity changes is called the point of inflection. So putting all these ideas together, we can come up with some shortcuts. We can say that when the derivative is positive, the original function will rise. When the derivative is negative, the original function will fall. We can also say that when the second derivative is positive, the derivative curve will rise and the original function will be concave up. And when the second derivative is negative, the derivative curve will fall and the original curve will be concave down. This little shortcut will help us a lot with our interpretation between the three curves, the original curve, the derivative curve, and the second derivative curve. So the second derivative will help us determine the concavity of the original function. Now, if I gave you this function and I asked you questions like, where is this curve have a positive derivative? The derivative is positive from negative infinity till about negative 2, from 0 to about 2, and from about 4.8 or so to about 8-ish. This is where the derivative would be positive. Where would the derivative be negative? Now, by the way, we know that the derivative is positive when the original curve increases. Where will the original curve, derivative curve be negative? The derivative curve will be negative where the original curve is decreasing from about negative 2.1 or so to 0, and then from about 2 to about 4.8 or so, 4.9, and then again from about 8 to infinity. Where will the second derivative be positive and the second derivative be negative? Well, we said that the second derivative will be positive when the original curve, the curve we're looking at, is concave up. So we're looking for points of inflection first here. So I would say we have a point of inflection about here at x equals negative 1, about a half, and then again here at positive 1 at a little bit more, less than a half. So we would say that the curve is concave up from about negative 1 to 1 on the interval from negative 1 to 1. This is where the second derivative will be positive. Where else do I have a point of inflection? Somewhere around here at about 3.5 till about here at about 6.5. The curve is also concave up from about 3.5 to 6.5. So that would be the interval where the second derivative would be positive. The second derivative would be negative on the interval from negative infinity to about negative 1, where the curve f of x is concave down, and from about 1 to 3.5, and from about 6.5 to infinity, all places where the original curve is concave down.